So, one of the monumental successes of or in theoretical and experimental particle physics is the prediction and the verification of the Higgs field. So, according to electroweak theory, at low energies, the photons, which are massless, and the W and Z bosons are not the same. So to account for the broken symmetry at low energies, the Higgs field is introduced. So the Higgs field, unlike the electromagnetic fields, is a scalar field. So it only interacts with W plus minus and Z bosons. So it was first introduced in 1960s, and so let's assign the Higgs field as this function phi as a function of position r and time. So say in this graph, in the x-axis, you have the value for the Higgs field, phi. So the Higgs field oscillates from minus phi naught to positive phi naught. And say we have our WZ bosons to be at low energies. So at low energies, they should be sitting around somewhere here or here. So Peter Higgs said that the mass of the W plus minus or Z bosons is proportional to the absolute value of the average of the Higgs field. So in this case, if they are sitting, say, here in this position, the absolute value of the average would be around phi naught here. Or in this case, if it's sitting here, the absolute value of the average of the Higgs field would be positive phi naught. So this is what we observe at low energies, or rather what we predicted at low energies. So at low energies, when the absolute value has a value, we know that the W plus minus and Z bosons would have mass, because the mass is proportional to the absolute value. So now we go to the high energies here. So if the particle sits here at high energies, it will oscillate from this value to this value. Hence, its average value in the Higgs field would cancel out. So if it is in this value, the negatives will cancel out the positives, giving it an average value of 0. Hence, the mass of the W plus minus or Z bosons becomes also 0, which is verified in that it acts like a photon. So this theory unifies the particle photon and the WZ bosons at high energies. So one way to verify the existence of the Higgs field is by detecting a vibration in its field, which is the Higgs boson. So the Higgs boson, its properties is it includes it is unstable, it has zero charge, zero spin, and it is a massive particle. So in 2012, CERN detected the Higgs boson with a mass of 125 GeV per c squared. And in the next year, the theorists who developed the Higgs field won a Nobel Prize. So this verifies the prediction that in electroweak theory, the photon and the WZ bosons become unified at high energies.